Hello. Okay, so I think we should start now. Well, again, if anybody see any instability of our network connection, just let me know. Well, either by using this chat, but well, maybe this chat will not works if my connection doesn't work well. So you can also use a WeChat, well, to notice me that something is wrong with my internet connection. Okay, and as long as we got the stock like yesterday, as long as we got one, then we will try to switch to WebEx. Okay. The reason I don't really want to switch to WebEx is simply because I think some of you don't like it, and I also think that it's kind of very annoying in some sense. Okay, so again, as I said, today, what we are going to do is first, we will try to discuss a little bit more about some interesting things. Well, at least I think will be interesting about the green function, okay? Which is something we didn't cover yesterday. We didn't cover it yesterday, and we like to talk a little bit more about the Green's function today. And then we will try to go through some typical mistake or problems in the homework 4, which is homework last week, okay? We'll try to go through some of the problems and discuss about that. And also, eventually, I will give you a very brief summary about what we've learned in this semester about the partial differential equation, okay? So what did we learn? And why this kind of partial differential equation is very important and is always, well, at least for people doing engineer, are always solvable, okay? So today, let's first discuss what is Green's function, okay? Just as the continuity of what we did yesterday. So at the end of yesterday's lecture, what we did is we got a representation formula for the solution of Laplace equation or harmonic function, okay, on the domain D, which is like 1 over 4 pi. You take the total integral over this, well, the boundary, the boundary of your domain, and you take the integral of this kind of thing, which is minus u at x partial n 1 over, well, x minus x naught plus you take partial n acting on u times, well, this would be 1 over x minus x naught ds, okay? So which means as long as you know what is ux and this partial n ux as the boundary, on the boundary, then we are able to find this u at any point of your domain, okay? So this is what we've learned. This is on 3D. On 2D, we just need to change this part to be some logarithmic function, okay? So this representation formula is very useful, at least looks very useful. However, and it's also very general because it's talking about any domain. For whatever domain, you just need to tell me the boundary condition of this harmonic function, then you can calculate this harmonic function. However, this may not be so useful simply because, well, if you want to solve a PDE problem, okay, like a harmonic function and in a bounded domain D, like Laplace u equals to 0 in D, okay? And then what you will be able to know is not two boundary conditions, but will be ux equals to some function f on the boundary of D, or this Neumann boundary condition is equals to gx on the boundary of D, okay? So which means if you want to solve harmonic functions problems on a domain, then this formula is not enough, okay? In practice, it might be possible, but in theory, it's not enough. You will only have one of these two conditions, okay? So which means, well, if we really want to solve a harmonic function, this formula does not close our problem, okay? It will not close our problem, find a closed formula. So then what we try to do is we would like to try to find somehow like a connection between these two terms and let one of this, for instance, this term eat the other term and make it a closed formula. For instance, we eventually write this ux norm is equals to something on the boundary only depends on this ux or only depends on this partial nux times some other function. Okay, and this is our aim. So that this kind of problem would be solvable for an arbitrary domain D. Okay, this is our well, intuition about what we are going to do today. Okay, so before I tell you what does this G looks like, any question? Any question?
I have a question.
Of course.
I'm still a little confused by partial U, partial N. Can you give an example?
Yeah, of course. For instance, as we mentioned before, if you have a domain to be the ball, the ball on the 3D, okay, this is your domain D, okay, then let's say the radius equals to 1, okay, then the boundary of this domain is actually equals to the sphere of radius 1, right? And then what is partial nu? Well, partial n in this form is actually equals to the normal vector of this domain, the outer normal vector of this domain times the gradient of u. Okay, on this partial D or on the boundary. Then this is a definition, right? This is a definition of partial n. Then the only question now is, what is this vector, right? And what is this vector? Well, okay, what is this vector? This vector is equals to, at this given point, is equals to what? It's actually equals to, it's actually equals to x, right? At a point x, you want to find the normal vector, normal, well, which means perpendicular to this ball, right? So, which means n is equals to x, right? At this point, the normal vector is equal, well, it's not equals to x, it's parallel to x. N is parallel to x, but n is a unit vector, right? So n should equals to x over the normal of x at any point x. Okay, so which means partial nu on this example is equals to x, well, over x, normalize this vector times the gradient of u at x on the boundary of D. So it could be very complicated, unfortunately. Sometimes it is complicated because n as an outer normal vector, it depends on the point you are, right? Depends on which point you take on the boundary. And but we can try to simplify it a little bit more, which is we can try to, for instance, if you have this kind of domain, like a ball or a sphere, and you try to take partial n here, then it might be simplified a little bit, which is, okay, so you try to take this outer normal derivative, well, outer normal vector, right? So if you try to do a change of variable, you change x, y, z to, well, you change x, y, z to r, theta, phi, which is so-called the spherical, well, which is so-called the spherical coordinate, okay, which is an analog of the 2D, of the polar coordinate, okay, on 3D. Then that becomes even simpler, because then if you try to check this kind of derivative, you find that this kind of derivative is actually equals to, well, x, 1 over x norm, the norm of x, times x partial x u plus y partial y u plus z partial, well, z u, right? By definition. And it's actually, you try to check, well, the change of rate of this u along this r direction. So it's actually partial u partial r, okay, by change of variable. Okay, so, well, so in this very special case, this well, partial nu can also be written as this form. Okay, so it depends. It depends. Well, maybe another example is if you have a square. Okay, then on the square, well, this is 1D. Well, I mean 2D. If you are in 3D, then maybe you will want a cube. Okay, this is a cube. Then you will have different kind of partial n, right? On different side, well, on different side, you will have different kind of partial n. For instance, let's say this is x, y, and z. Okay, and then, well, let's say what is, for instance, what is a partial n on this side? On this whole side, what is partial n? Then you can see that on this side, your n is equals to, again, very simple, right? It's actually equals to 1, 0, 0. You just have, well, let's say this is x, this is y, this is z, okay? Then on this side, on this part of your domain, of the boundary of your domain, n is equals to 1, 0, 0, okay? Then partial u partial n is equals to n dot gradient of u is actually equals to ux. Okay? And similarly, on this side, on the top of your cube, your partial n, this is 1, and on 2, your partial n, similarly, is equals to uz. Okay? But on the other side, for instance, on the bottom part, this is 3. On 3, this n will becomes not really 0, 0, 1, but now it becomes 0, 0, minus 1, right? So on 3, partial u partial n is equals to minus uz. Okay? Maybe this will be an easiest example about what is partial u partial n. And similarly, you can get what is partial u partial n on this side, this side, this side, this side. Okay, all the side of your cube. Okay.
Okay, thank you.
So basically, it will depend on your real problems. So for this kind of things, it will be always given. Okay. For a physical problem or a math problem, it will be something doable. Well, at least computable, and it will be something that will be given, at least in our course. So let's go back to our problem. Again, we want to eliminate these two conditions to one conditions, right? To a simple condition, a simple formula like this, like this. Other than we'll ask you for 2 boundary conditions, we only want 1, because otherwise the problem may not be well defined. Okay, so here what we are going to do is we will define so-called the Green's function. The Green's function gx x0 for, well, operator, let's say minus Laplacian. Well, we always say the operator minus Laplacian to mean that, okay, you have this Laplace equation, okay? And it could be some other kind of operator. In the future, you will see, for instance, might be minus Laplacian plus I, which is you trying to study, well, the solution to Laplace u equals to u, okay? Or minus Laplacian plus partial x. Yeah, this part we just well, for this partial n, well, you will have to know that, because this kind of partial n is something I assume you know. Otherwise, well, we don't really know. We don't really learn a lot of things in this semester, because, well, Dirichlet boundary condition and Newman boundary condition are 2 very basic boundary conditions, and you better know. Okay, but for the Green's function, it will not be on the exams, and it's just for fun. And it just for in the future, it might be useful for you. Okay. And for Green's function, we are talking about the Green's function of this operator minus Laplacian. It may not be something else. It could be something else, but then, well, it will call the Green's function for some other operators. Okay. You can also check this kind of thing as keywords in the future if you have to deal with this kind of problem. So we have the operator and the domain D, okay, at point x0 in D is a function such that, well, it's a function of x, and x0, we assume it's kind of a fixed point. Okay, it's something fixed. It's a function such that it satisfies the following 3 conditions. First, gx or gx(x0) is second order continuously differentiable. But it's not differentiable everywhere. And Laplace g equals to 0 in D, but it's not differentiable everywhere. It's not continuous everywhere. It has some exceptional point, except at x equals to x0. Okay? So the Green's function is some kind of mimic of this 1 over x minus x0. Okay? It's kind of saying that similar to this 1 over x minus x0. And so that we have to expect this kind of operator will have a singularity at x equals to x0, just like 1 over x minus x0. Okay, you will see that the Green's function will always somehow looks like 1 over x minus x0 plus something very smooth. Okay. Moreover, as we said, it will have the corresponding good boundary condition. For any boundary point, the Green function has to equals to 0. Okay, so that it is well, kind of saying that is that will not confuse you. Okay, on the boundary, this g should equals to 0. And thirdly, this is something like, like what I said. This Green's function is just some modification of 1 over x minus x0. Okay? Gx x0 plus 1 over 4 pi x minus x0 is finite at x0 and has, well, continuous second derivative everywhere and is harmonic at x0. Okay, so which means if you take out this part 1 over x minus x0, then the Green function is nothing but a very, very nice function except on the boundary. Okay, the Green function is actually a harmonic function everywhere, but it does not have any good boundary condition in this case. Which is why I say that it's more or less like, well, you're trying to do some modification of 1 over x minus x0. And, well, this kind of modification will makes it, makes this part of your representation formula to be able to observed by this this first term. Okay. On the other hand, you can also think, as I mentioned last time, well, you can, if you are able to solve this kind of, if you are able to understand what is a generalized functions, well, you may think Gx0 is a solution to this differential equation, to this partial differential equation, which is you take the Laplacian. It's actually equals to, well, not really 0, but delta x x0 or delta x minus x0. Okay, so which is everywhere 0 except at x equals to x0. And Gx x0 equals to 0 on the boundary. Okay, so this is the idea. But of course, in this course, it's actually a little bit beyond this course, because if you try to understand it mathematically, what's the meaning of this this kind of system, you will need a little bit more knowledge about the functional analysis. Okay, but whatever. Well, this is so-called the Green's function, and well, one very interesting point is this kind of Green's function always exists as long as your domain is not so bad. Not so bad means where your domain on the boundary of your domain is not as bad as this kind of very zigzag thing. Okay, as long as your boundary of your domain is somehow regular, then the Green's function always exists on this kind of domain. Okay, this is something I would like to let you know, because this part, if you want to prove it rigorously, then again you will need to know a little bit about holomorphic function and what is holomorphic map from one domain to another domain. Okay, and then you can see that as long as you have a Green's function on some domain like the ball or the upper half plane, then you will able to construct the Green's function any kind of domain. Gotek's derivative, what's that? I haven't heard about this term before. I'm sorry. But, well, okay, anyway, so this is our definition of Green's function. But then, well, the question is why Green's function is something that can help us to solve the problem. How can we use the Green's function to get some, well, some compact or closed formula for our problem? This is something very interesting, and the theorem is just as I stated before, which is the Green's, well, the representation formula for harmonic function can be simplified or make it as this kind of thing, which is something that only depends on one single boundary condition. Okay, on either 3D or 2D. If you want higher dimension, then it's also fine. You can get, well, something similar like this kind of formula, but with this kind of singularity part of your Green's function may be slightly different. For instance, on 4D, this will not be x minus x0. It will be x minus 1 over x minus x0 squared. Okay, and on 5D is 1 over x minus x0 cubed. And well, for harmonic function, you can always write it as ux times this Green's function, gxx0 ds. Okay, so which means the Green's function is a very good thing. As long as you know what is a Green's function of a domain, you are able to solve the Laplace equation on this domain. Okay, given the Dirichlet boundary condition. Well, the proof is very short, so I would like to just write it. So you know that we have the representation formula. Let's say V is equals to 1 over, well, minus 4 pi x minus x0. Okay, this is your V, just for simplicity. Then we have, by the representation formula, we have U partial n V minus V partial n U ds. This is our representation formula. Okay, we have the representation formula, and now we want to get rid of this term. Okay, how can we get rid of this term? Well, we know that G, as long as you subtract this V, right? If you subtract this V x0, you will get a super nice function. Let's call it H, okay? x0. You will get a super nice function H such that H is harmonic, but not, well, equals to 0 on the boundary. Okay. Well, then actually H on the boundary is equals to, well, 1 over 4 pi x minus x null, right? For x in the boundary. Okay. H is not so nice, but we still have this Green second identity, right? Which is some Laplacian, well, Laplacian H, we take that B equals to H on the second Green second identity times U minus Laplacian U times H. Is it still equals to on the boundary? Okay, U partial H partial N minus partial U partial NH. Yes. This is a Green's second formula for U and H. We have this formula. And you can see that Laplace H and Laplace U are both equals to 0. So the right-hand side equals to 0. Okay. We have this formula. This guy equals to 0. You also have this representation formula. This guy equals to x, 0. Okay. Now, let's try to use, let's say this is 1, this is 2. Let's use 1 plus 2. Then, what we have is ux0, this is something on the left-hand side, plus 0 is equals to, well, the first term is u times partial h partial m plus partial v partial n. Yes, partial h partial m plus partial h partial v partial n. It's partial g partial n. Okay, minus partial u partial n h plus v. H plus v is equals to g. We know that G satisfies 0 boundary condition, right? G on the boundary, it is 0. So the second term disappears. So we get this. We get this formula very easily. Okay? So any question about this? Any question? So this means as long as we are able to find this kind of, as long as we are able to find the Green's function on the domain D, satisfy 1, 2, 3, the 3 properties. As long as we got this 3 properties function, then we are able to solve our Laplace equation on any domain. Okay? The logic here is, well, what we're trying to do for this second part of our session is we try to solve, we already solved this Laplace equation on the disk. Okay? Then we learn very hard on this, Fourier transform. So as long as we have known what is Fourier transform, we also know what is the Poisson kernel on the, upper half plane, right? And then we are able to solve the Laplace equation on the upper half plane. Disk, we know how to solve it by Fourier sequence or the Fourier series. Upper half plane, we know it from, Fourier transform or Fourier analysis, right? The Laplace equation. Disk, we learn it from the Fourier series. This upper half plane, we learn it from the Fourier transform. But now we are tired of this kind of tricks, so we want to get something in general. What happens if your domain is something very, very weird, not very regular? And here, we finally get some kind of properties about the solution of this Laplace equation on this kind of domain, which is as long as you can find the G for me, then I can solve the Dirichlet problem for any domain. Okay? This is the idea. And in practice, to find this kind of domain is not very easy. It's something doable, but not very easy. You will know that as long as you know, as far as you learn this complex analysis next semester. But in general, it's very hard to find. And so in practice, if you really want to solve a Laplace equation, a harmonic function in general or in for some particular domain that you want, you better try to check the reference. Somebody will just solve this kind of Green's function by their hand. So you can just try to cite their book or reference or literature, and then that's the end of the story. You solved the PDE, the Laplace equation on that domain. Okay, for instance, on cylinder, or the Green's function on cylinder, the Green's function on the rectangle, the Green's function on, for instance, on the annulus, the Green's function on some kind of weird shape, cone, this kind of thing, you can always find it from the literature. Okay, and so which is why I think this kind of thing will be important for you if you really try to solve the problems from practice. Okay, and well, I think another thing I would like to talk a little bit about is some physical intuition about the Green's function. Okay, Green's function is a function satisfies these three properties, and the Green's function actually also has some physical meaning, which one of the most important physical application is, well, in electrostatics, when you try to study the electron on the space, okay, then you may wonder, for instance, you have an electron at point x0. Then what can we know about the electric potential caused by your electron, this one single electron? What is the potential of this x0 at some point other than this x0? Okay, and in this kind of area, you will know that, well, it will depend on the domain. It will really depend on the domain about how you can compute on each point what is the electron, well, what is the potential, electric potential of this, well, given by some electron putting on x0, okay? And this Green's function is actually, it's the electric potential inside of conducting surface S equals to partial D due to charge at a single point x0. Okay, so it does have the physical meaning. It is actually the electric potential, which is why you can imagine, which is why at x0, if you try to study, you put an electron here and try to study what is the electric potential at this point, then it's actually infinity. Okay, and also on 2D and 3D, you have different kind of decay of this, well, electric potential. Okay, and then from physics intuition, okay, physical intuition, what you can imagine is there is so-called the principle of reciprocity. Okay, which is something like the Newton's third law. Okay, which is saying that, okay, suppose you have 2 points, then you put 1 point here and try to check the effect of this point at this point. Okay, this is x0, this is x1. The effect from x0 to x1 is actually the same as the effect from x1 to x0. Okay, so which means the electric potential at x1 due to x0 is the same as the electric potential at x0 due to x1. Okay, so mathematically, this means for Green's function, we will always have a property like this. Gx1 x0 is equals to Gx0 x1 for any x0 x1 in D. Okay, this is something from physics, and this is also something you can prove mathematically. Okay, so is that understandable? There's no math here. Well, at this moment, okay, it's just some physics. And interestingly, well, we definitely can prove it mathematically, but well, this proof, I just wonder whether I should show you the proof or not. Well, maybe I'll just show you the proof very roughly, and so that you will get an idea about how we can think about this problem. Okay, so and well, I would like to show you the proof simply because, again, the proof is very standard method in math, which is like the cut and paste, and then which is why it might be a good exercise for you to try to train yourself, okay, in analysis. And the proof is like this. Well, you want to say that, for instance, this is point A, this is point B. You want to say that this GAB is actually equals to GBA, right? You want to show this. But this is not very easy to show. However, what you can try to think about is you try to let U to be GXB. Maybe I will just let this to be V and this to be U, GXA. Okay? And then let's try to, because you can see that this two U and V, this green functions has singularity at A and B, right? It's more or less like 1 over x minus B and 1 over x minus A. Okay? So which is not so nice around the point A and around point B. So instead of domain D, let's consider the domain D, subtract these two balls, two epsilon balls. Okay, so this we call it D epsilon. We do a 2 cutoff about the domain, and then the domain becomes well, so-called a surface. Well, this is not 2D, this is actually 3D. But if it is 2D, then this is so-called the surface of genus 2, right? So you will get D epsilon. Then the good thing is on the domain D epsilon, your U and V are both harmonic function, so you can try to use the green second formula or the green second identity. Okay? And then you will see that, okay, the boundary integral, basically, if you try to do it like this, then the boundary of D epsilon is actually the boundary of D union the boundary of B epsilon A union the boundary of B epsilon B. Okay. So is that clear? So the boundary becomes, well, this outer side and this part, the boundary of this part and the boundary of this part. Okay, so is that clear? Then by the Green's second formula, what you will have is, well, the boundary integral, this Euler boundary integral, u partial v partial n minus v partial u partial n, plus the, well, the same part on epsilon a will be epsilon a, and the corresponding part on b epsilon b. Okay, is equals to the integral, the spatial integral on d epsilon Euler plus v minus v plus u, which is 0. Right? Is that clear? Is that clear?
Why,
Well, what?
I think I missed something. Sorry.
Oh, what's that?
Like, why is this one? Like, why is this integral equals to 0?
Well, because by Green's second formula, it's equals to the epsilon Euler plus v minus v plus u. Right?
Uh-huh.
And you know that this is your u, this is your v. They are both Green's function, and we do a cutoff so that the Green's function becomes harmonic. It has no singularity on d epsilon.
Mm-hmm. Oh, okay.
So it's equal to 0.
Got it. Thank you.
Okay, so then what we do now is, okay, you will have this part, you will have these two guys. Okay, and well, the nice thing here again is we use the property of Green's function, right? If we use that, we know that this u on the boundary is 0, v on the boundary is 0, right? So the first term also disappears, right? Because u on the boundary is 0, v on the boundary is 0. So a epsilon plus b epsilon equals to 0. Okay, is that clear? So we got something very similar as before, as what we trying to show some kind of, well, Green's representation formula, okay, which is this a epsilon is the integral x minus a equals to epsilon. This is your sphere, u partial v partial n minus v partial u partial n ds. Okay, and b epsilon is similar, well, similarly is x minus b equals to epsilon, and the similar c. Okay, and then you can argue just like what we did before. And if you argue just like what we did before, you'll find that, okay, v is actually, well, near this a0, well, v, well, I mean, u near this a can be written as something like 1 over 4 pi r with minus sign plus some good function, and v near this b, it can be written as 1 over 4 pi r, Ra, Rb plus h. H is a smooth function, okay? Ra equals to h x minus a, Rb equals to x minus b. Near a, near b, or on this B epsilon A or B epsilon B. We can write this U and V in terms of this kind of thing, this kind of function. Okay? Then, by the same argument, like we try to show this representation formula, you can see that as epsilon goes to 0, A epsilon equals to U A, U B, and B epsilon equals to B epsilon equals to VA. It's minus sign. Okay. No, I'm sorry. This is something wrong. This should be VA because you will have this V will this U will disappear. Yeah, this term will disappear, and this will be minus UB. Okay. So VA. Sorry. So VA equals to UB, then GAB equals to GBA. Okay? It's just a similar idea as we show in this representation formula. Okay? You just shrink it, and every other term it just disappear. The only thing that left would be okay, this U0 or UA term, or UB term or VA term. Okay, anything else will just tend to 0. So if you are not clear about this, you can try to check your textbook, okay, on stress book. This is kind of technical, but it's very interesting and it's very, well, useful in terms of analysis, this kind of idea. So you can prove that, well, this electric potential given by this point B at A is actually the same as the electric potential given by A at point B. Okay, you have this symmetric principle. Any question about it? Any question? Okay. Then, based on this kind of intuition, this physical intuition, we can actually do a little bit more than this. Okay. Well, by the way, so actually, what we can do, what's more we can do is, if you have this inhomogeneous problem, you can actually somehow play with it and make this part appropriate by solving this Green's function. You can actually make it somehow okay so that you can still write the solution to this PDE, okay? Which is, this part is still like this part. And you will have something left as Laplace U, okay? Fx gx x dx. This you can get it from G2, okay? Because why we got this kind of thing from this in addition to this kind of thing, you have these terms. It's simply because this will be Laplace U times G. Okay, so if Laplace U equals to 0, then this term disappears. But if Laplace U is not equal to 0, then you will have this term left. Okay, so similarly, getting from G2, you can get actually for inhomogeneous problem, the solution should look like this. Well, I just mentioned it here. Okay, and I'll introduce you more applications of physics. Application of physics in Green's function. Okay. Well, this is something I think very interesting. How you can use the physics to math in order to solve some PDE. Okay, this will be something really useful, and I think it's very interesting. Well, for instance, although we solved the PDE on the upper half plane, okay, we already solved that, but then is that possible? Since we already know this language of Green's function, the method of Green's function, can we recover our results for the Green from the language of Green's function? And well, is that possible? Or what can we get if we use a Green's function? For instance, what happens if we have the half space instead of half plane? Well, for the half plane, you get something similar. Okay, I'll leave it as an exercise for you. For half plane, you get a very similar Green's function, and that is, well, after you do the calculus, you find that that's exactly the same as what we find by the Poisson's formula. Okay, and now let me show you how to find the Green's function for half space instead of half plane, which means what happens in 3D. Okay, for 2D, it's actually the same as 3D, and you can get it by yourself. Okay, and you can then recover what we have done for the Poisson curve, similar to this Green's function. Okay, for half space, well, let's introduce this notation. If you have a point x, y, z, then the reflected point x star, let's name it as x star, is just a name. Reflected point is x, y minus z. Okay, so which is, if we are interested about this, well, upper half space, which is z, this is x, y, z, which is z greater than 0, then the reflected point of a point on this space is the, well, is a symmetric point on the, well, about the xy plane. Okay, and then you can actually compute the Green's function by the reflected point. The Green's function for upper half space is gx(x0) is equals to, well, you have this first term minus 1 over 4 pi x minus x0 and plus 1 over 4 pi x minus x0 star. Okay, what does this mean? Well, this kind of formula is actually from the physics. At least, well, you can understand it from physics point of view. You have this coordinate g at, well, this kind of thing is what? This kind of thing is you put one electron at point x0, okay? And the electric potential, well, from this electron is given by this form. Okay, but then you find that, okay, then you may have a lot of well, electron potential, but then it's not the Green's function. It's not the Green's function because then the electron potential on this xy plane is not 0. Okay, so it's not the Green's function because for Green's function we really want the electron. Well, you have some electron and then you give this kind of zero boundary condition. Okay, so how can you put some electron so that it can make this xy plane with electric potential 0? Okay, so the idea is you can put, for instance, you can put a positive electron potential, where electron at this x0. Then what you can do is you can put a negative electron at the point x0 star. Okay, the reflected point. Then magically you will find that the potential at xy plane, the electric potential at xy plane is 0. Okay, why is that? Well, it's simply because if you choose any point on this xy plane, then, well, by the definition of the reflected point, we have the distance between this point and x0 and the distance between this point and x0 star are the same. Okay, so the potential, the electric potential at xy plane at this point is equals to 1 over minus 1 over 4 pi x minus x0 plus 4 pi x minus x0 star, because one is positive, one is negative. Well, maybe I should put this as negative, this as positive. Okay, as electron potential. And we know that this and this at xy plane are the same. Okay, so it's actually equals to 0. So which means the electric potential at xy plane is 0. Okay, if you try to put one positive or negative electron at x0 and the one negative or positive electron at x0 star, then what happens is at this xy plane you don't have any potential. Okay, this is a reason why gx0 will on the upper half plane, upper half space is this guy. Because it is harmonic, the distribution of the potential of electrons satisfy the harmonic function, and it satisfies the zero boundary condition. It makes the electron potential, electric potential at the boundary equals to 0. Okay, and you can actually check 1, 2, 3 is satisfied. Okay, it satisfies the requirement of the property 1, 2, 3 of the Green's function. Another example. This is an example for the half plane, half space, and another example is for the sphere or for the ball. Okay, again 3D. You have a sphere, okay? Then now let's take the cross section of the sphere, which is the circle. That makes the drawing a little bit easier. Then again, we will have this kind of similar things, okay? A very similar reflected point, a very similar definition of reflected point of a point, say x0. you will have a reflected point at x0 star. Okay, but this will be somehow different, which is, well, we want, but well, the effect are the same. Okay, the idea are still the same, which is you put in, well, maybe positive or maybe negative electron at x0, then you must be able to put another negative or positive electron at x0 star, so that on the boundary of your domain, you don't have any electric potential. Okay, then where should you put this x0 star? Given x0, where should you put this x0 star so that it can cancel all this potential, so that you get your Green's function? That would be the problem, right? That's actually a physical problem. And you can actually, well, you can actually show that this x0 star is a point so that, well, this center of your disk and x0, center of your ball and x0 star are in same line. Okay, they are in the line. They are in the same line, and you want x times x star equals to exactly r squared. Okay, so that you can show for any point on this on this sphere, this and this will have, well, after you do the calculation, it will be well, the potential will be 0 at this point. Okay, this is just some geometry, and I don't really want to do it. Again, you can check it from your textbook. Okay, why this part and this part, this distance and this distance will give you the same potential. Okay, the same electric potential. And so that your Green's function at the 3D ball, well, or S2, or maybe I should say B3 is equals to minus, well, 1 over 4 pi x minus x0, okay, and plus a over x naught. Well, a is a radius. I don't really want to use this r as radius because we use this r to be a variable. So let's say a squared. Let's say the radius is a. Okay, a over x0 times 1 over 4 pi x minus x0 star. Okay, and this is your Green's function for a 3D ball. Okay, and moreover, maybe I should mention this in 2D. For a 2D disk, okay, we will have similarly gx(x0) is actually equals to 1 over 2 pi, instead of 4 pi, it's 2 pi, log x minus x naught, minus 1 over 2 pi log, well, this will be, again, let me write it in another line, subtract 1 over 2 pi log r0 over a, well, x0 over a, x0 over a times, well, this is x minus x0 star. Okay, and interestingly, you will see that, okay, this is G, right? So then the ux0, again, we can write it as, well, the boundary integral is equals to something like, well, on the boundary of this sphere, or on this x equals to a, okay? And you will have this, well, ux on the boundary partial n gx x0 ds. right? So what does it look like? It will be the derivative of this logarithmic function, right? You take the derivative of logarithmic function. So, which is why eventually, after you do the simplification, you will find it's actually eventually equals to a minus x naught squared divided by 2 pi a. You take the integral, x equals to a. hx, let's say u on the boundary of this ball is equals to hx. hx divided by x minus x naught squared ds. Okay, and if you check the Poisson formula we find, it's exactly the same as this one. Okay, so we recover the Poisson's formula or the solution on the disk on 2D, the formula of that, by the Green's functions method. Although it looks a little bit complicated, but you can see that eventually they are the same, and the difference is just up to some calculation. Okay. So that's basically all I want to introduce to you about the Green's function. And you can see that in the future, if you are interested, you can also try to study a little bit more about this kind of Green's function, because that will be useful. But but I would recommend that, well, in the future, if you really need to do this kind of problem, at that time, at least you would remember that, okay, what kind of keywords I should search from the internet? Oh, it is Green's function, okay? If in the future you want to solve the Laplace equation on some kind of weird domain, then, well, you will know that you have to solve it by doing this kind of, Green's function, okay? So that you at least have this keyword. Well, maybe I forgot. There's one more thing I would like to mention, which can be leave as an exercise for you, which is, well, I mentioned that you know that, well, for the upper half plane or the half plane or half space, and for the sphere are only two examples that we try to deal with, right? And we don't really have any other kind of Green's functions or the method of the Fourier transform or Fourier series, right? So this looks a little bit weird. So what if we have some other kind of very regular, well, piece of shape, and we're trying to find, for instance, the Green's function of that? Well, for instance, what if we would like to find the Green's function on this kind of square? How can we find the Green's function of this square? If you try to use this kind of physical method to find the Green's function, that will work, definitely work, okay? But then you will find that then the Green's function may look not so nice. The reason is, suppose you have an electron here, a positive electron here, okay? Then that means, okay, the potential of this electron, well, must be able to write as this is x0, 1 over 4 pi x0 minus x0. Okay, this is a potential. So if you want to make all these four sides to have zero potential, then how can you make it? Well, the easiest way from the idea of our reflected point is, okay, it should be somehow looks like our upper half plane. Okay, upper half space. So maybe if we want to make this line in 2D, if we want to make this line, maybe I shouldn't. Well, if it is in 2D, then that shouldn't be this one. It should be 1 over 2 pi log x minus x naught. Okay, this would be the potential on 2D. If you want to make this line potential 0, then you have to put the x0 star. Say x0 star. Maybe let's call it x1 at this point, which has the same difference as the same distance to this line. Okay, to this this line L1. Okay, and we put a minus electron here. so that the electric potential at L1 is 0. So you should, well, minus 1 over 2 pi log x minus x1. Okay. However, that's good. That makes this line, this L1, potential 0. But again, we want to make this, well, L2 potential 0. Okay. Well, this might be slightly different from what we thought, right? Because if you want to cancel all the electric potential on L2, then what you want to cancel is all the effect from x0 plus all the effect on x1, right? So if you want to put somewhere like x2 as a minus electron, then it will depend on x0 and x1, right? So you may want to subtract something else, x minus x2, where x2 may depend on x0 and x1. Similarly, if you put an x2 here and a negative electron here, then the potential on L1 now is not 0, right? Although it may change a little bit, but it may not be 0. So which means in order to cancel it, you may want to put an x3 here. You want to put an electron at x3 so that to cancel the effect of x2 on this L1, okay? And so on. So which makes the problem slightly harder than we thought, right? And if you check the literature, you will find that the Green's function for the square or for the rectangle are always like infinite series, unfortunately. So, which is why I'm saying, well, if you have some regular shape or even something, if you have some kind of shape, or even something very regular, the Green's function may still be very complicated. Although eventually you may find that, okay, you don't really care about whether it will be complicated or not. But mathematically, you'll find that, okay, it's not so easy to find everything. Okay, so this is, well, last thing about the Green's function I would like to say. And well, now let's have a short break. Maybe before that, any question about this part? Any question about this? If no more question, then we will have a short break. Any question? Okay, so that's basically all I want to share with you about the Green's function. And let's have a short break, and we will resume at 30, okay, 4:30. And on 4:30, we will start to deal with our homework and do some review. Okay. How could I?